Hello, everyone. Good morning. Uh, Welcome to Cisco Research and Outshift Summit on Quantum Security and Post-Quantum Cryptography. We have an exciting set of sessions today, and we're going to go over the cutting-edge advancements in the world of post-quantum cryptography from several distinguished speakers. The agenda would follow as the following. We'll invite Dr. Ramana Kompella, Cisco Fellow and Head of Cisco Research, to kick off and introduce the topic to all of us. Then myself will speak about on one aspect of PQC. And then we'll have Dr. Dustin Moody from NIST PQC to talk about the NIST PQC project. Then Professor Elisa Bertino from Purdue is going to talk about quantum resistant networks. Professor Attila Yavuz from University of South Florida is going to talk about national infrastructures and then quantum safety. And Dr. Jaideep Vaidya, who is a distinguished professor at Rutgers University, he's going to talk about trustworthy IML in the post-quantum age. And Professor Cristina Nita-Rotaru, professor of Northeastern University, is going to talk about quantum disruption with respect to blockchain. Following that, we'll have an exciting panel discussion among all our speakers, and it will be open for Q&A. So stay with us. Let me invite Dr. Ramana Kompella to kindly deliver his talk and open the summit.
Thank you, Ashish, for setting this up and inviting all these distinguished professors. We have an amazing list of talks, and I'm really looking forward to getting a deeper understanding of what people are thinking about when it comes to quantum resistant infrastructure of the future. And let me start by maybe sharing my screen, saying quantum and quantum computing is actually pretty much around the corner. It used to be the case that quantum is perpetually 10 years out, decades out. But over the past few years, if you look at the number of advances that are happening in the quantum arena, it's just accelerating at a rapid clip, right? So with big companies like Microsoft, Google, IBM, announcing pretty good advances in quantum computing infrastructure. In addition to Cisco ourselves, we have been announcing the quantum networking of the future. So with the advances in quantum computing and quantum networking, I think it is safe to say that the quantum future is actually very much around the corner, and the time to actually build a quantum computer or a quantum supercomputer that can actually break existing cryptography is actually not that far out. So I think this session and this summit is actually pretty timely because we are pushing the world to prepare for this quantum threats, and the time to actually migrate to a lot of quantum resistant infrastructure is actually today. And that's actually the title of my talk. I think this is a quick timeline of a lot of activities ever since 1980s to where we are. I think we have had about 50 years of quantum computing proposals and algorithms to sort of shape this. But only recently, right, only a couple of years back, have we seen NIST actually publish the post-quantum crypto standards that will prepare us against the famous Shor's algorithm and and Grover's algorithm that can break existing cryptography. And ever since, I think the whole world is really trying to migrate to these standards, and rightfully so, because we really need to be prepared for this post-quantum threats. So briefly, I think, I think this is like general knowledge, but like, I'm just gonna go over this. Shor's algorithm can break RSA and key exchange protocols like Diffie-Hellman. And Grover's algorithm provides quadratic improvement on symmetric cryptography. So you can actually effectively think of a key of size x as x over 2. So in this case, AES 128 is equivalent to perhaps AES 64 with some additional maybe constants. But the bottom line is a lot of these crypto standards that have been the workhorse of classical cryptography are under attack with the help of, they'll all get like, either broken or weakened with the help of a quantum computer. But the imminent threat is actually the harvest now, decrypt later, which is around, attackers actually just storing packets, waiting for a CRQC to be invented, and then go ahead and decrypt all these packets. So whatever information that is flowing today is potentially vulnerable to HNDL if we assume that like maybe a CRQC is not that far out, let's say 5 years out, and if your information is really if your information longevity is actually longer than that, that means it is safe to say that, like, your information that is already on the wire will potentially get compromised. And this is the reason we have to worry about these attacks now because of Moscow's inequality. I mean, loosely speaking, if X is the amount of time to sort of migrate to a quantum resistant infrastructure, and Y is the longevity of your information, if the time to invent a quantum computer that can break this cryptography is less than X plus Y, that means you are in trouble, right? And hopefully, and if it is greater than that, then that's fine. But so in other words, if there is already information, if you assume that the quantum computer that can break cryptography is 5 years out, and your information longevity is 10 years, then already like the information is potentially compromised. So the bottom line being, we have to worry about this stuff right now. In fact, yesterday, for many of the many of the information or types of information that has longer shelf life. And there's a lot of other factors that are driving urgency, like government mandates, customer demands, competitive pressures, and so on and so forth. I want to just punchline again, safe to say that the time to worry about quantum threats to classical infrastructure is today. And the only thing I want to say here is, we often, I mean, and so, Ashish actually kind of introduced this, right? He started off saying quantum security and PQC. So a lot of times, people sort of conflate PQC with quantum security. PQC is a tool in the toolkit to actually get to quantum security. But when we really think of quantum security, I think there are a lot of facets to it. We kind of think of quantum resistant security in a somewhat holistic manner with three key tenets. So number one, crypto observability. So this is actually around figuring out what types of crypto you're actually using that potentially may have post-quantum vulnerabilities. Okay, so this could include your applications. You could do a static analysis of your applications and figure out what type of crypto libraries is it actually importing. But just because an application has quantum safe crypto libraries imported doesn't automatically mean that it is actually speaking quantum safe on the network, on the wire, because of version downgrades and there's also crypto suite negotiations and stuff like that. So you have to holistically observe, right, which portions of your infrastructure are actually quantum safe and quantum unsafe. And the other thing is, oftentimes we sort of think of only the packets that are traveling on the wire, which is actually one of the, I would say, easiest threat vector for an attacker to attack or exploit. But there is also the product side of the equation, which is your server, your secure boot, your keys that are embedded within the server. Okay, so these are all right now vulnerable to quantum attacks as well. So again, observability is all about taking an inventory of what types of crypto you're using in your infrastructure and what type of attacks are they actually vulnerable towards. The second piece is actually around crypto resilience. More broadly, I think this is a very classic, well-known concept in security called defense in depth. Quantum resistant security can only be achieved through true quantum resistant security can only be achieved through multiple potentially levels of defense. This doesn't mean if I mean, of course, one level of defense is always better than none. So at least start with adopting post quantum crypto standards. But post quantum crypto standards have been around for a handful of years, and the amount of scrutiny that they have gotten is pretty high. But who knows, right? So maybe that there is a quantum algorithm of the future that can potentially break post quantum crypto or at least weaken them. In which case, you would want your infrastructure to be ready for potentially other forms of defense. So that's actually the second pillar, which is around what are all the types of defenses that you can come up with to make sure that your infrastructure is quantum resistant. And finally, and this is a piece where I think Ashish is going to spend quite a bit of time, but I think that a lot of people talk about agility and crypto agility, but I think it's a very important area where I would say broadly crypto agility is around figuring out how to sort of de-ossify your software and not intertwine or hard bake your crypto libraries into your software so that when you need to swap crypto, right? So crypto is just a workhorse for encryption and decryption. Your software, the business logic of your software should be ideally decoupled so that your crypto libraries can be swapped without actually having to completely abandon your or do a major surgery on your software. And that's actually crypto agility. And this actually is an area where I feel like because we are already investing in this migration from existing crypto to post quantum, I think this is an area if we invest, we would be a little bit more future proof. And I think together, observability, resilience, and agility form the pillars of your holistic quantum resistant security strategy. And I'm hoping that we will see a lot of research and more innovation around making all of these things faster, easier to consume, and hopefully the toolkits necessary to actually get to these will improve over time, and there's some really good open problems in this space. So with that, I'd like to end my talk, and over to you, Ashish.
Thank you so much, Ramana, for the kickoff and also taking us through the framework of holistic quantum resistant security. So I think as part of the agenda, there's me next. Um, so I'm going to talk about software-defined cryptography agility. And as Ramana pointed out, this is an important pillar. But before that, I'm going to quickly go over our efforts at Cisco Research and Outstripped, which is not only helping Cisco across different activities, but also with academia. We have a lot of collaboration, and we're trying to develop a framework for the industry for PQC migration as well as quantum security. So we have a number of publications. The only few of them are listed here. One of the key ones that came up recently was the quantum cryptography co-evolution. There's an archive, and I'm not going to all of them. And then the latest one where you can use lightweight machine learning, classical machine learning, for classifying implementations of cryptography primitives. That has been accepted at SCM SACMA just a few days back. That is for black box techniques, and then also there are a host of work. I'll not go into that. We've had number of invited keynotes and talks between at Cisco Research and at academia as well as at the industry level. We are also organizing a number of academic conferences as well as summits. So the next one, last year we did a workshop at SCM CCS on QRSec, quantum resistant security and cryptography. And this year we are doing a SCM SIGSAC conference. This is the first year of PQQS that will be held November 2 to 4 in the Bay Area. Our working group members and the chair is Professor Elisa Bertino, and the members are Cristina Nita-Rotaru, Jaideep Vaidya, and Attila Yavuz of the working group for quantum resistant security for networks, where we are developing different approaches and best practices. So we are all together developing that conference, PQQS conference, as well as working on developing some best practices. So I want to say thank you to our academic collaborators as well as to our Cisco senior leadership team and all our Cisco colleagues in research, Outshift, and across, because they have been wonderful in supporting this work as well as absorbing some of this work for taking Cisco as a quantum security leader in the industry. Now, let me go over, I don't think I'll have too much of time to go over all the details of software-defined crypto agility, but quickly, essentially one of the key challenges is, if you look at the threats, right, CRQC threats are going to be there when CRQC is going to be realized, and we are moving very fast, and the latest timeline from Google is about 2029. And imminent threat right now is the harvest now, decrypt later. But there's an intermediate threat. We call that as transitional post-quantum threats. Or what they are is that anytime, and that will remain for as long as the quantum threats are there. Anytime there's a PQC is not widely adopted, or PQC is adopted but its implementation, its configuration, its use is not properly in place, or legacy systems where PQC cannot be adopted, for example, different hardware devices or systems. There are transitional PQC threats, PQ threats, and how do you address all of them in a holistic manner? And that is then the next point is that PQC standardization is nice, necessary, it's important, but it's not sufficient, because cryptography can only go this far, but how you use them, and you need other defense in-depth measures. So how do you account for new threats and new remediations as you are seeing coming up in the community, right? So therefore, the holistic quantum resistance requirements are that how do you attain quantum resistance, how do you operate in a quantum safe manner, and how do you remain flexible to new threats and new remediations, So that is where the framework that Ramana presented a few minutes back was about having crypto observability, crypto resiliency, and crypto agility as the three pillars working in tandem across them to provide operational quantum safety. That is for the networks, for data and assets and infra, are going to provide a trustworthy quantum resilience platform. And then several years of work, we feel that this is the optimal set of requirements that we need to implement to support both not only today but also the future of quantum security, because we need to have forward quantum resistance, not just a quantum resistance for yesterday or for today, because the threats and new remediations are going to come up, new techniques are going to come up, new cryptography protocols are going to come up. So how do you support that? So enabling forward quantum resistance or loosely forward security, we need crypto agility. So Darwin, talked about that. Who is going to survive? It is the most responsive one to change is going to survive. It is the one that is most agile and adaptive is going to survive, and that is where where crypto agility comes in. So software ossification, is somewhere you have legacy code, okay, or the code that is already being written or you're going to write today, tomorrow. They actually have software constructs about or cryptography artifacts. They're already embedded in an ossified manner, in a more of a, sometimes they are kind of, if I can call it, quote unquote, hard coded. It's like you want to use RSA or you want to use ECC, or AES 128 bit, for example. They're all invoked from the business logic itself. And therefore, to be able to be agile, that creates a problem. So how, the question is, how can you architect software such that we can deossify it, we can embrace the new crypto protocols without disruption, right? That is, and therefore we are proposing the concept of software defined crypto agility, where provide code, quantum risks, and context. It could also be configuration policies, whatever. The software defined crypto agility system is going to lead you to a policy, a control plane, a crypto control plane that manages the cryptography aspects. It's kind of going to be provider for cryptography primitives and all the details, their implementation to the business logic, to the data plane. That's the crypto consumer. And the PQC and security policy is going to drive how they are, what specific cryptographic protocol is being used by the data plane. But the data plane doesn't implement any cryptography protocols. That's the goal, and that is how we'll be able to, in a modular manner, in a seamless manner, be able to manage different adoptions of different cryptography artifacts, algorithms, libraries, protocols, or not, during the software development, during the deployment, as well as during the runtime. So we want to decouple, then update the data and application plane. That will then the cryptography implementations and settings move to crypto control plane, and the policy and config plane supports the the PQC compliance or quantum security compliance. Okay, so for example, we'll take a set of classical code. Here, take this, that it starts signing a message, okay, and it signs the message using hashing, and then using a RSA 2048 bit key. Now the parameters are hard coded. It is hard coded to use RSA in the application, and the specific padding is also included, hard coded there in the application. Right now, imagine trying to make it agile or flexible, so that in tomorrow when there's a new protocol that we need to use, like MLDSA, can we use it here? So this is where we want to deossify the crypto implementation. There's a config, which is the policy aspect, policy and config aspect. Then there's a crypto control plane that is now taken out from the application, and this is the business logic, which will work with the crypto control plane and the config together to consume the crypto artifacts. So the solution is that then how do you do this deossification? What is the secret sauce there? And with the concept, with the we've developed a crypto agility co-pilot using agentic AI. See, AI is everywhere, is helping us a lot in automating a lot of stuff, and we thought, why not? So we have been using AI for PQC for more than 2 years to 3 years now. Now we take, basically on top of the software defined crypto agility foundation, we have developed this copilot that will take a specific set of code and then generate the software defined artifacts, crypto control plane, provider, crypto consumer, this data plane, and then the policies automatically, all seamless, in a seamless manner. So given this time I have, I think what I'm going to do is that I'm quickly go over the 4 phases of software defined crypto agility. You take the software code, either specify or extract them, and then you refactor it to crypto versus non-crypto using program slicing or static analysis. And then you carry out crypto deossification, and then you generate crypto agile code. Okay, and that could also involve how to protect from CRQC threats, how to protect from HNDL, how to protect from transitional threats as well. Okay, I'm not going to go into all these details. What I'm going to do, provide is try to see if I can give you a demo. So before that, the summary is that we have looked into the quantum crypto co-evolution very clearly and in a more detailed manner, and that shows that new quantum threats and new remediation techniques are emerging, are going to emerge. This is, I'll call that is a golden era for cryptographers, and also security folks, especially for quantum security. Now, crypto agility is going to support quantum resistance in a forward secure manner. And our approach with software defined crypto agility and the implementation is the Cisco Research Crypto Agility Copilot. It's a research prototype at this point. So let me try to see. I'm going to take the red pill here and go to the live. Let's see if it's going to work. Yeah, it worked. Okay. All right. So this is a live demo, and I'm going to, there's an implementation of the code that I'm going to provide, and we're going to do static agility. There is also dynamic agility, but I'm going to do static agility, and we're going to make this code crypto agile. Okay. So it's working. Okay. It downloaded. Let me download the package here. Right. So let's see. Okay. Okay, so this is the DFU. So okay. Let me first delete the first one, one. Yeah, I think we got the DFU one. Okay, sorry. Let me share my screen. Apologize. There was my bad. Okay, thank you. So Okay, I'm going to redo the demo again. Okay, let's see. Verification. Okay, for the, because I think it was not visible. Okay, I hope you are able to see the demo now. I'm going to download the package. So this is this one ends with sorry, 9F8. Okay, so okay, now here we have the control plane. Let me try to open this with uh, okay, terminal. Let me just to show. Okay, so this is the so this is the crypto control plane that has been generated right now. Okay, and let me pause here. I'm not going to go into more details here, but if you see, if you see here, let me go into that. So we have the business logic, that is a main business, then the control plane, then the crypto policy is there. Now let me show you the crypto policy. Okay, the crypto policy has quantum risk is low. For now we can change that, and then post quantum is MLCAM, and classical hardened is RSA. So and the business logic aspect is going to is a very simplified. It doesn't really implement any crypto artifacts here, just uses them. We can change the quantum risk to high, then it will start using the MLCAM implemented in the control plane. Okay, and it uses the control. All right, so that was my demo. Thankfully it worked. So all the information here actually is future functionalities, that these are research prototypes. There's a disclaimer. Any questions for me? Okay. Okay. Next, I'm going to hand over to Dr. Dustin Moody, and thank you so much, Dustin, for joining us for the summit. And Dustin is the PQC lead at NIST, which is the primary driver for the post-quantum cryptography since 2016 or even before that. And thank you so much, Dustin, for your time. So yeah.
Okay, thank you. Hopefully you can see the slides and you can hear me and everything, and appreciate the introduction and the opportunity to tell you a little bit about our post-quantum cryptography standardization project that we have at NIST. At NIST, there are a huge number of scientists working on a variety of different topics. The area that I'm in, we deal with cryptographic standards. That means we write the actual standards themselves. We also do a lot of research that's geared towards cryptography. We provide guidance on how to safely use cryptography in various applications and have documents to explain that. And we also have a testing and validation program. But pretty much any device that you are using is likely using cryptography that has been standardized by NIST. We already had a nice introduction on the quantum threat, so I don't think I need to belabor this very much at all. Quantum computers are being built by many different organizations and governments. They have a phenomenal increase in computational power for certain applications and problems. They won't be universal and replace everything that our classical computers do, But it's because of this benefit that they will be a boon to society and to scientific research, and do a lot of very cool things that will make all of our lives a lot better. It is a challenge to build them. That is why we do not yet have a quantum computer that is really large. People are actively working on this and making progress. Cryptographers, though, have been worried about one of the aspects of quantum computers due to these two algorithms that have already been mentioned. The first of these, Shor's algorithm, it's amazingly, it solves two different mathematical problems that don't appear related at all. The second algorithm, Grover's algorithm, is a bit more generic, and we see the impact that they have cryptographically with regard to some of the standards that we have at NIST. So at NIST, our standards are put into documents called FIPS, Federal Information Processing Standards, or SPs, which are special publications. I have a chart here showing kind of some of the different types of cryptography. There's public key base, there's symmetric key, and then there's other, tools that we have like random number generation and so on. Amazingly, Shor's algorithm, if you were able to run it on a large-scale quantum computer, it would completely break every single public key crypto algorithm that we have standardized at NIST. This includes algorithms like Diffie-Hellman and RSA, as well as the elliptic curve version of the Diffie-Hellman and the elliptic curve digital signature algorithm. And it would completely break them. We couldn't simply scale up to a new security level. The algorithm is so efficient, we need to, just quit using these algorithms. Grover's algorithm would also have an impact on the cryptography that we have, but it would be a little bit less dramatic. It would mainly be targeted towards the symmetric key algorithms. These are block ciphers like AES or hash functions like SHA-2 or SHA-3. And rather than having to completely get rid of the algorithms, at most what we would need to do is use longer key sizes or longer hash outputs, which that is manageable. If you need to go from AES 128 to AES 256, it's a longer key, but you're already using that algorithm, so you can likely handle that. Now, when will this threat be here? When will a quantum computer be built that is large enough that will threaten current levels of cryptography? Of course, since this is a research question, nobody knows the answer to that. The best we can do is we can ask some experts, and this chart here I'm showing is from a report issued by Dr. Michele Mosca and some of his colleagues. Every year or two, they do a survey to experts in the field, and they ask them just this exact question. When do you think a quantum computer will be built that is big enough to break RSA 2048 in 24 hours? You can read the whole report. They actually just came out with a new one, but this shows a summary of the main findings. When these experts were asked, will this happen in 5 years? Just a small percentage thought it was possible, between 5 and 14%. Now, while that's a small chance, I mean, think about that. If that actually occurred, it's greater than non-zero. That would have such a big impact. If all the cryptography that we use could be broken in 5 years, or at least all the public key algorithms. If you go out to 10 years, the percentage that these experts predict rises, and if you go out to 15 years, they now feel it's closer to 50%. So this just gives you some sort of the the time scale to be thinking about when we might have a quantum computer. It could be as short as 5 years. It could be 10 years. It could be 15 years. We don't totally know. While that is unclear, there are some things that are clear, and this was already referred to. With the harvest now decrypt later threat, you need to be migrated to a new solution well in advance, because your adversary, your enemy, could have already harvested your data, made a copy of it, and is simply holding on to it, waiting for the quantum computer to come along. We know it takes time to design new solutions to replace the ones that are vulnerable. We know it takes time to evaluate them and gain confidence in their security. We know it takes time to standardize them and then to migrate to the new solutions. So even though the threat is uncertain, what is certain is that we have a lot of work to do to ensure that we migrate well before the risk to our data. The name of this field has been given is referred to as post-quantum cryptography. And just to clarify again, these will be algorithms which are run in classical computers, just like we have in software today. They won't be running on quantum computers or quantum hardware or need quantum devices, but they have to protect us against attacks from both classical and quantum computers. Back in 2016, NIST had been well aware of this threat and had been studying this problem when we kicked off a big international competition to select new algorithms that would replace the vulnerable ones in our standards. NIST has done this sort of thing in the past, where we've harnessed the talents of the cryptographic community worldwide to design new algorithms, and evaluate them, and ultimately gain confidence so that we can select some for standardization. And it's been very, very successful in partnering with them. Here's a timeline showing some of the, the steps over the past 10 years. I'm not going to go through all the details. There was a huge number of submissions that were sent in. They were whittled down through a process of evaluation, both internally at NIST and externally. There was a lot of research done at trying to break these schemes, doing performance benchmarking. Ultimately, in 2022, we announced 4 algorithms for standardization. And it took us 2 years to then write the standard, get public comment, and publish them. But in 2024, we had the big milestone when we released the first PQC standards. Since then, we have had 1 additional algorithm that has been selected for standardization, so that we now are at a total of 5 algorithms. So these standards are in documents that are called FIPS, which is Federal Information Processing Standards. They're in FIPS 203, 204, and 205, and what will be FIPS 206. There are 2 different functionalities that were targeted. With our public key standards, we needed key establishment, or equivalently encryption, and then we also needed public key digital signatures. So for the key establishment, we selected MLChem as the primary algorithm that we want people to use. It's based on lattices and has really good performance and security. As a backup to that, we also have an algorithm called HQC that will be coming out in draft form later this year. For the digital signatures, we have 3 different algorithms that were selected. The primary one that we recommend that people use is FIPS 204 MLDSA. It's also a lattice-based algorithm. SLHDSA is a kind of a backup that's not based on lattices. It's bigger and a little bit slower. Security-wise, it's viewed as more conservative. And then, if needed, FIPS 206 has FNDSA, which is an algorithm with smaller signatures, but the implementation is very complex. It needs floating point implementation. That draft is hopefully coming out very, very soon. So while there are options, again, we recommend MLChem and MLDSA to be the main PQC algorithms that you standardize. And both those were published, almost 2 years ago. We are still evaluating a few other candidates for potential standardization. The main reason for this is we want a better backup algorithm than SLHDSA, which its performance isn't too great if you needed to use it. So currently there are 14 candidates being evaluated. These, again, primarily will be sort of as kind of backups to MLDSA. This will go on for another year or 2, maybe even 3, at the end of which we might select 1 or 2 of these signatures for potential standardization. And we don't have any similar process planned for the key establishment side of things. So with the standards already being out there, the focus has shifted over the past year or 2 a lot to be worried about the migration to the new algorithms and the transition, and what do organizations need to do that. The United States government has been taking action to ensure that it will be prepared, along with its federal agencies, and issuing guidance that anybody can follow. So we've seen national security memos come out. The National Security Agency has put out what's called CNSA 2.0 for national security systems, which require a higher level of security. Congress has passed legislation to make sure that all agencies, are following this guidance. The goal of the United States government is shown in this quote in the bottom left here. As much as possible, we want to migrate our high priority and high impact systems by the year 2035. And even though that is 9 years away and it might seem like we have plenty of time to get there, in reality, cryptographic transitions take a long time. And so I highly doubt we will be completely done by the year 2035. It's going to be a very complex, difficult transition. To facilitate that, NIST issued a report known as NIST 8547 that shares some perspectives on the transition to PQC. It also has timelines that are needed to migrate by. These are in support of the US government's goal of 2035. The document also, it specifically calls out what are the quantum vulnerable algorithms in our NIST PQC standards, and what are the PQC standards that you need to move to, which I already talked about them. The timeline, if you're at the 112-bit security level, which we hope you've already migrated off of that by now, but if you haven't, those will be deprecated in 2030. And all of the public key algorithms, the classical ones, RSA, Diffie-Hellman, ECDSA, those will be disallowed after 2035, and you need to have migrated to the PQC algorithms by that year. I will point out the timeline for the transition is only affecting the public key crypto algorithms. The symmetric key algorithms, AES, SHA-2, and SHA-3, as long as you're using at least 128 bits of security, you can continue to use those algorithms. There's been a lot of interest in migrating in a hybrid fashion, and that's the idea that because these PQC algorithms and their implementations are a bit newer, maybe we want to combine these with an existing algorithm that we have experience with, and combine them in a safe and secure way. And this is known as hybrid. There's some advantages to doing this. Security is obviously increased. You'd have to break both algorithms. On the negative, if you're doing two algorithms, there's going to be a little bit more performance hit that you have to take, and things are a bit more complex. So there's some trade-offs. This isn't going to be right necessarily for every organization or application. NIST isn't recommending either for or against it or mandating it or anything like that. We want to accommodate it. We want to make sure people can do it safely if they would like to. And importantly, we point out how you can get FIPS 140 validation if you want to use hybrid, as long as one of the schemes that you use is a NIST standardized algorithm, and it'll need to be a PQC algorithm, by the year 2035. So you can find more guidance on that in SP 800-227. As I mentioned, NIST does have a testing and validation program. This is done through what's called our cryptographic module and algorithm validation programs. FIPS 140 testing. There's an automated testing system that there's a link to you can go to, and vendors that have implementations can submit their implementations to some accredited labs that we have around the world. The PQC algorithms are available for testing. This was ready to go once the standards came out, so there's no need to wait on that. So that's an important resource for many vendors to know about. In addition to facilitate the migration, NIST has what's called the National Cybersecurity of Excellence, which has been running a migration to PQC project, where we have teamed up with a lot of great companies around the world that are all partnering with us to work on the migration. And they're sharing best practices, they're testing each other's solutions, they're writing reports together to share what they've learned along this process, all to support the standardization. And that has been a really successful project. And I'd encourage you to check out their webpage for the information that they have there. They also have a really great FAQ page where they've pulled together guidance and resources, not just from NIST, but from other organizations and internationally on the migration to PQC. NIST is not the only standards organization, of course. There are other ones that deal with different layers, different protocols. NIST is working with most of these standards organizations or participating and communicating with them. Most of them have taken the algorithms that we have standardized, or sometimes algorithms that were in our process that we didn't select, and making standards for some of these algorithms. In particular, the IETF has a lot of work going on right now. ISO is also doing international standardization. We've also seen countries around the world have been selecting algorithms for their use or providing guidance for industry in their countries, which is a good thing, and we've had a lot of coordination with that. There are many things that organizations can do to prepare for this migration. Again, it's going to be a complex journey. It's not going to be accomplished overnight. One of the first things you're going to want to do is do a cryptographic inventory to find out where your information and assets are that are being protected by cryptography. Which algorithms are you using? Which data has the longest security lifetimes that you need to protect that data for? You need to be talking to your vendors to find out what their migration plans are. So you're going to need a team with a leader who's got resources, who's building a roadmap for your organization to do this, and making sure that this is all going on and is receiving appropriate attention from the leaders in your organization. With that, I'll wrap up. Some good resources for you are our PQC page or the NCCOE page. If you'd like to kind of keep up to date with announcements and standardization news, we have what's called the PQC Forum. It's a mailing list that you can sign up for. Instructions how to do that are on our webpage. And yeah, I'll wrap up here. If there's any questions, I'm happy to answer them now or a bit later on when we have more time. So thank you.
Thank you so much, Dustin. I think we are running a little bit late, so maybe we can move on to the next speaker and then have the questions answered for Dustin in the panel session.
Sounds good.
Thank you so much, Dustin. So our next speaker is Professor Elisa Bertino, distinguished professor at Purdue University, and she's also our chair of our working group on quantum resistant networks. Professor Bertino is going to talk about quantum resistant networks beyond cryptographic substitution. Thank you so much, Professor Bertino, for your time and for presenting at the summit. Over to you.
So I'm going to discuss not just how to replace cryptography that we today use, but how to design techniques and processing ensuring that networks remain secure as cryptography evolves. As Ramana has already mentioned, those cryptographic algorithms, even the ones which are being standardized, may prove to have vulnerabilities in the future. So we must be able to withstand those changes and evolve over time. So this talk is based on our recent work on systematizing post-quantum network architecture. And of course, we already have mentioned which are the issues. I would like just brought by quantum computers. I would like just to mention that public cryptography is a very critical component. It underpins a lot of protocols, security protocols that today we use. Therefore, the quantum crypto threat will be a systemic one. And what is really worrying today is that the timeline is accelerating. We are seeing fewer qubits needed to break cryptography compared to many years ago. Very important is improved error corrections and more concrete estimates, which are moving the time when we will see those quantum computers being used to the early 2030 or even sooner. So the question is not if, but how we prepare system on time. And when looking at the solutions, of course, there are two alternative solutions from the crypto point of view. The first is a solution that I call physics-based solutions, where basically you use a quantum cryptography. The second is what I call the mathematic-based solution. And this is the one which bases crypto on some mathematical problems that quantum computers cannot break. And those are typically called the post-quantum cryptographic algorithms, and the ones being standardized by NIST are in this category. And in the rest of my talk, I'll focus on the second category, mainly because those are started being used, and there is a lot of research and actually standardization activities starting using these type of techniques. And but the problem when we transition, during the transition and even after, could be that both approaches will be used for different components and segment of our network. So the problem will be really very complicated. But our point of view is both approaches basically focus primarily on cryptographic primitives, not on systems. And typically we see, for example, a lot of effort focusing on protocol substitution, like post-quantum TLS, but networks are very complex systems. And there are a lot of aspects that we need to deal, like a key distribution, trust, life cycle of key management topology. So the core question is, how can networks achieve cryptographic agility during and beyond the post-quantum transition? Because again, the future, there will be new attacks, new algorithms, and so forth. And so the key question becomes that agility is not one-time migration. It is the ability to adapt as assumptions in cryptography change over time. So therefore, we have a very complex design space, because achieving cryptographic agility is not a single solution. It is a design space of architectural choices. It's not just algorithm, it is a system problem, and we end up with trade-offs. And to kind of have an idea of the space of those solutions and the aspects, we came up with a taxonomy which basically organizes the design space into several dimensions, 7 of them. And for each dimension, we identify possible solutions. For example, dimension 1 lists the possible cryptographic foundations. But we also identify open research issue, open research direction. And I won't have time to go over all of them because there are a lot, but I can assure you there are a lot of issues that we, both the research, industry, academia, standardization bodies needed to address. So let me just give you an overview. The first is a cryptographic foundation. This is the cryptography that we are going to use. The second dimension, which is very important, is key distributions. Once you have those keys, especially if you have symmetric encryption, we need to understand how to give these keys to different parties that need to communicate. The third dimension is the type of threat that we need to address and the type of trust assumptions that we have. For example, do we have a trusted authority, or we don't assume a trusted authority? The fourth dimension, which I think is very important, is more a process, I would say, is the key management life cycle. Because when we deal with keys, we have a life cycle. We go from generating key, distributing, using, and they, for example, we use different keys for signature, for encryption, the scope of use of the key. Rotation will be is very important. Where do we store those keys? And again, if we store them in trusted hardware, we need also to deal with attacks on this hardware. How do we recover from keys being compromised? Of course, the deployment and operational model is also important, because a different type of application domain may have different requirements, and they may require different strategies for post-quantum agility. And so you can see, we have identified a number like enterprise and data center, interscale, IoT, and so forth. The 6, this is focused, the dimension number 6 focuses exactly on the network layers and protocol and topology. Here we go into the core network and see which type of post-quantum algorithm techniques we may use depending on the layer of the network. And finally, the security properties. So which type of properties do we need to focus, do we need to assure, and so forth. I just now give a very short overview of some of those dimensions. And the first is a cryptographic foundation. So we have identified 4 classes, but there could be more. And again, I want to emphasize that our taxonomy may be expanded. We came up with 7 dimensions, but there could be more. And so, of course, the first approach is symmetric one, which will work well as long as we have enough longer keys, because they are robust, and somehow our colleague from NIST just mentioned about this. But they require a strong life cycle and key distribution services. So we needed to distribute those, which was not a problem with public key encryption and cryptography. And then the second technique is the one based on the, I would say, the NIST proposed algorithms, which are based on post-quantum public key infrastructure, public key encryption. This is scalable because somehow it's like a PKI we had before. There are issues about the fact that those signatures are very large. And just to give you one example, we did one experiment using one of the NIST standardized algorithm, specifically the one for signature. I've used the dilithium 2 to just do a very simple signature. When you connect, when your phone connected to a cellular base station, it has to receive some message, which is called the a system information block. And this contains physical parameters allowing the phone to, to establish the communication channel with the cell tower. And together, actually, with Professor Attila Yavuz and his students, we did the experiment to show, try to sign this broadcast message, which, by the way, has to be sent very frequently. And it is a broadcast message because it will go to all the phones which have to connect. Well, our experiment was that this key required 3,732 bytes, and which basically this signature had to be split into 13 separate packets, because when you look at this message format for this system information block, this has only a very limited free space, 290 bytes, in which you could put your signature, but the signature is too long. So which means you have to fragment the signature in 13 packets. The phone has to combine them back. Of course, it's not feasible. So this is just one example in which we have real-time constraints and a lot of limit on the use of the spectrum. In general, network provider don't like using a lot of spectrum for security tasks. Then we have the hybrid. This was already mentioned by the presentation in NIST. This is very interesting, is defense in depth, because when you combine a lot of different techniques, you need to defeat all of them if you are an attacker. There are a lot of issues related to complex composition and coming up with security proofs, mathematical proofs that the composition is correct. I mean, has some security property, and also failure model. Other approaches which are interesting are multi-path, in which you basically distribute the information on different channels, and this in theory has a stronger secrecy because it's information theoretic secrecy, but depends a lot on path-independent assumption. Of course, we found a lot of research issues just on those areas, and we just list a few, like hybrid security guarantee, symmetric only scalability, how we scale the symmetric to very large networks, algorithm agility versus interoperability, how we manage evolving post-quantum standard. And again, before there was an interesting point that said that different countries, organizations are coming up with their own algorithm. Somehow RSA was used everywhere, but now everyone will use their own. So even interoperability will be very complicated. And the other problem is side channel resilience to a PQ implementation scale. Here I want to point out that post-quantum algorithms, especially the lattice-based ones, have a very different characteristics compared to classical crypto. They have large keys and ciphertext, more complex arithmetic operations, and non-uniform memory access patterns. Those properties can make them more vulnerable to side channel attacks, such as timing attacks, cache-based attacks, power, or electromagnetic leakage. And this can be a problem when you deploy those algorithms at scale. The other second important dimension is how we distribute those keys. And this is the key distribution architecture. Indeed, if there is a place where cryptographic agility truly becomes a system problem, it is in how we distribute those keys, how they're managed and refreshed. This also deals with the life cycle. There are many architectural models. First, centralized the key distribution, such as KDC-based system. And those are attractive because they're efficient, simple, and well understood. But they introduce a single point of failure. They are a high-value target for attack. And they typically provide weak forward secrecy. Hierarchical architecture. In this case, the key distribution is organized along the domain boundary. For example, enterprise of telecom hierarchies. They scale very well and align with organizational structure, but they introduce a different risk, which is a compromised propagation. So if higher level node is compromised, that can affect an entire subtree. So scalability, here we have scalability, but at the cost of increasing the blast radius. Third is threshold or multi-party computation-based architecture, where trust is distributed across multiple entities. There is no single node which holds the full secret, but operation require a lot of coordination, and this may introduce a lot of latency. And finally, we have a multi-path, which again, minimal trust assumptions, but depends on network topology. Also here, we have a lot of interesting research issue. For example, in the multi-path, you have to have this secure orchestration and so forth. Other dimensions are the trust and threat model. Of course, this depends against the type of attacks you want to defend. Some potential attacks are typically whether against, for example, partial compromise of key, attacker able to quantum attackers, long-term traffic recording capabilities, partial control of a network infrastructure, including routing and key management component. And therefore, one has to understand which type of trust one have and which type of attacks. The life cycle is particularly critical. And I would like to mention a very important aspect, which especially because I realized that the rotation of key may be very important. And I didn't realize that the rotation was so important. Then while trying to work on this taxonomy, I realized that there was. So typically what happened here, this is particularly relevant when we deal with symmetric encryption. So what happened here that the Grover algorithm can improve brute force attacks against symmetric encryption. However, the improvements are not particularly strong, and therefore just reduce, basically only gives a quadratic speed up for brute force attacks. And therefore, if you change the key very often, by the time the attacker can break your key, you have already changed the key. But frequently changing the keys and rotating the key is not easy, is an organizational problem. And there are, of course, we need efficient large-scale rekeying, even recovery after compromise. So basically, trust assumptions fundamentally shape security and must match the threat model. Post-quantum security requires very good processes for managing the key. The other, of course, area which is very important is the deployment and networks. As I mentioned before, depending on the environment, you may use different solutions. Examples are, for example, for enterprise, cloud, scalable, PKI friendly, could be good. So there they can adopt, post-quantum resistant public key infrastructure. With I/O and Edge, we have a constrained and symmetric encryption. The problem could be the very, very small device may not even be able to store a larger symmetric key. And for 5G, 6G telecom, hierarchical distributed key distribution can be an interesting approach. For industrial critical infrastructure, threshold and multi-party computation approaches for distributing key can be an interesting approach. And finally, we have a more disconnected, intermittent adversarial environment. And again, we have some solutions that may be better, but this, of course, requires a lot of analysis. We require to talk to companies, users in those environments. Finally, again, we have for networks, and we have different techniques that we could use. The key challenges is that, as already we mentioned, is that there will be heterogeneous post-quantum readiness across the system. So today we have the notion of zero trust architecture, and that can be useful in helping. The same notion can help segmenting the networks of the system according to different readiness with respect to post-quantum. If you want to use a multipath, you need to ensure the independence of the path, and there will be always a trade-off that we already saw in our work on cellular networks of performance versus security trade-off. So security is also important, and we have many properties like a perfect forward secrecy. So if a key is compromised, past transmissions are not compromised. How do we deal with the post-compromise security? And how we deal when some key material may be compromised. And of course, we need to resist to network level adversary with different types of capabilities. But properties, in our case, depend not only on the protocol, because protocols, like especially encryption, cryptographic protocols, people do proofs of their security. But in our case, the entire security depends on the architecture. And hybrid and multipath design change the guarantees, and system level and protocol level guarantees may be very different. So you may have an algorithm which has a certain security guarantee, but when you deploy in a certain system, the system may not have the same level. So basically, security properties are emergent and depend on many factors, and they are not automatically inherited from the primitives. To summarize my presentation is that no single dimension is sufficient, trade-offs are unavoidable, and architecture determine long-time resilience. So as I mentioned before, post-quantum transition is a continuous adaptation, not a one-time upgrade. So this concludes my talk. I would like to thank all my colleagues which are involved in the report that we prepared, on which my presentation was based. And with this, I'll end my talk and stop sharing.
Thank you so much, Elisa, for an amazing talk and taking us through all the dimensions. In the interest of time, we have our next speaker, Professor Attila Yavuz from University of South Florida. He's an associate professor and has been working on post-quantum cryptography for several years, I think more than a decade or so. And his area of work is primarily applied cryptography, and he's going to talk about deployable, breach resilient, and quantum safe critical national infrastructures. Thank you so much, Attila, for your time and joining us for this summit. Over to you.
Right. Thank you very much for a great introduction and the opportunity to present my work in this excellent event. Thank you very much. So today's talk will be about deployable, breach resilient, and quantum safe critical national infrastructures. A little bit about my research. I focus on post-quantum cryptography, primarily with the applications of secure next generation critical networks. That will be the primary part of this presentation. And time remains, I will also touch upon the intersection of all these three, including secure AI. So in this presentation, the main theme that we will be talking is a series of federally funded medium to large scale projects about quantum safe critical national infrastructures. One collaborative project that I will mention will be about distributed and post-quantum secure next generation wireless networks. And in this project, we aim to answer the research question, how to make wireless infrastructures such as 5 and 6G, and especially public key infrastructures, resilient to breaches and also post-quantum secure. Another project that I will touch upon is a one of its kind international project between NSF and Swiss National NSF, and it focuses on quantum resilient satellite and terrestrial networks. There we are considering how to make satellite and terrestrial integration, particularly quantum safe and also scalable. And finally, another project that I will be briefly touching upon is the work with Army Research Laboratory that focuses on ultra lightweight post-quantum cryptography for IoTs. How can we make good old IoTs both large scale and also sufficient for low-end IoT systems? And if time remains, I will briefly touch upon an ongoing project about trustworthy collaborative learning in distributed critical infrastructures. This one is about cancer detection and prevention with post-quantum security. So let's begin. The first project that I will mention is distributed computing in effect towards trustworthy, post-quantum resilient, and secure next-generation mobile networks. This NSF project is led by USF, collaborative between OSU and Virginia Technology. So here are our research challenges that we wanted to address. One of them is the breach vulnerability, usually stems from the centrality. Let's consider the public key infrastructures. As Professor Martino mentioned, they are a very important angle of any communication networks. Let it be the commercial transaction, or you wanted to just perform any cryptographic operation, we have to certify the public keys, and public key infrastructures are doing that for us. However, it has been shown many times if a PKI is compromised, especially root keys, it impacts tens of millions of users. And this problem has been there for a very long time, and it is still here even with conventional cryptography. Another issue that these are relevant is the mobility and handover overhead. So imagine a vehicle driving on the city. How many times different cellular providers and base station this vehicle has switched? Every time it switches, a new cryptographic overhead to come. And this is again very expensive and relevant in PKIs, even with conventional cryptography. As Dustin Moody has mentioned, the quantum computers will invalidate existing infrastructure that focuses on elliptic curve cryptography and RSA. And then obviously the question is, can we replace all these things with NIST post-quantum cryptography standards and be happy? What we observe is that if we wanted to make public key infrastructure distributed, you need to use threshold cryptography. And it has been a challenge even with conventional techniques. If you wanted to do that with NIST post-quantum standards, they are not designed to be executed in distributed way. So we have to find another way to do this. And obviously, again, if you are using elliptic curves, an elliptic curve signature will be at best 256-bit overhead, half kilobyte, let's say, without point compression. If you want to do that with MLDSA, you start with 2 kilobytes. And this is a very signature, a very heavy overhead we have to consider. So our goal is, can we achieve distributed security, do this with standard compliance, and do this with post-quantum safety? These are the overarching goal of this proposal. So if we move to our solution space, the main algorithmic contribution will come creating optimized MPC techniques, secure multi-party computation. And we are currently focusing on innovating NIST post-quantum standards with MPC. Our recently accepted IEEE security and privacy paper is an example of this. You may remember the MLDSA that Dustin mentioned. So we are taking it, integrating with MPC, and put on a public key infrastructure to show you can both be compliant to this standard and also become distributed. So when you do that, our solution space can be expanded to achieve some interesting properties. Now, imagine that instead of using just one central authority, we achieve that different central certification authorities, such as VeriSign, that of Microsoft, all can come and collaborate with together to create alliances. Very similar to airline alliances, right? For the benefit of their customers, they form alliances, and we all benefited from this. Can we do the same thing with certification authorities? Thanks to MPC, they do not have to expose their secrets, which is a good incentive for them. And thanks to this, now customers do not have to trust only one of them. If one of them is breached, thanks to MPC, we will be breach resilient, that we are also achieving. And another thing is that now, instead of a vehicle to communicate, let's say 50 different CAs, now handover may consider potentially 5. And this will also bring down the overhead substantially. So these are some new properties at the architectural level we can achieve once we are utilizing our algorithmic innovations. And finally, algorithmic and architectural, also at the hardware level, our collaborators are working on making these things side-channel resilient, which is very important. And overall, the combination of these 3 innovation vectors, the intellectual merit includes over 15 publications until now, 2 patents. Some of them are including spying and spoofing resilience wireless communication backbone, the ones that Professor Bertino mentioned for 5G authentication. Others are applying these things to secure multi-party computation, and even some at the physical key layer generation. Overall, when we integrate MPC with NIST PQC, Dustin would mention NIST is looking to expand existing standards into distributed domain that are called from the NIST. So this project aims to fill this gap in that perspective. So this is one project that we are focusing on distributed computation and quantum safety. Let's move to the another one. In this one, we are focusing on satellites. So it is post-quantum resilient cybersecurity fabric for integrated satellite terrestrial network called SATUC. This is a collaborative project with Switzerland, Zurich Applied Institute of Sciences, and between us. And let's see what research challenges we are trying to address. When we consider satellites, one of the biggest issues, obviously, consider a geosynchronous satellite. Standalone transmission introduces a lot of delay. On top of that, due to the exposure of space, package loss and reliability issues always has been there in satellite networks. So even without any cryptography, there are performance and reliability issues. And when you add to classical cryptography, many of the existing satellite systems are currently not enjoying conventional cryptography at all. And now, as we have discussed, those satellite systems are protecting GPA, broadcast authentication for military, and many levels of civilian applications are obviously has to be long-term, because once launched, we want them to be in service over a decade. Therefore, these systems has to be post-quantum secure, yet, especially as European Union emphasizes in every point, unfortunately, this is not the situation for current infrastructure, and this is a very important gap. Here, I will give a throwback to Professor Bertino's presentation. She mentioned when you put a post-quantum primitive, package fragmentation reaches up to 13 times, right? So that was in the ground. Imagine when you are doing this on a legacy satellite network. The package fragmentations and impacts on the network protocols will be very substantial. So this is a big research challenge at the cryptographic and algorithmic level. So another very big challenge will come in terrestrial integration. So mostly when we consider about satellites, we think about GPS and location services, but data orbital centers for artificial intelligence is coming to ensure free cooling that space may offer is one example how cloud infrastructures will extend to the space domain. So many machine learning and AI algorithms for achieving federated learning are getting benefits from satellite backbones. So as we can see, a very serious integration effort between satellite and terrestrial networks are under the way. And when we do so eventually, this will open the Pandora's box and bring a lot of attack vectors. A compromise on the one part of terrestrial backbone now can impact many other parts globally due to this space-terrestrial integration. And it is a topic that we need to think about. Finally, algorithms and architectures are all here, but at the end of the day, the performance analysis is also very important. The NS3, the famous network simulation tools and similars, has been considered for some small-scale systems, but when it comes to satellite and terrestrial integration and post-quantum security, we are not aware of the availability of such solutions, and therefore this is also an important research gap to be considered. In this direction, the overarching goal of this federal project is to create, to the best of our knowledge, first resilient satellite terrestrial fabric in the post-quantum era. So how do we do this? The technological backbone, again, will be distributed computation and new authentication protocols. So what we wanted to propose is, if we are to focus on terrestrial components, let's create a distributed key management core that will provide access control and lightweight cryptography at the distributed level. When that happens, many key distribution, derivation, and management that terrestrial network would support satellites now become breach resilient and also post-quantum secure at the same time. One technical example is, imagine we are broadcasting a signature with MLDSA dilithium, formerly known. Most of the time, this will come with a certificate chain and some pre-computed commitments as well. Why don't we use terrestrial infrastructure to distribute these extra artifacts and do so with a distributed architecture so that if terrestrial network is compromised, we will not be compromised. But thanks to these optical infrastructures on the ground, we do not have to transmit very large number of tokens over the space, substantially reducing the overhead. What about using advanced protocols such as Tesla, which requires time synchronization, but achieve key disclosure not from the space, from the ground? It is okay because in the ground, we will not rely on single entity. Again, we will rely on distributed infrastructure. By integrating novel authentication protocols and distributed computation, we are observing that we are able to substantially reduce the overhead at many levels. Until now, project led 5 publications and 1 patents focusing on scalable post-quantum command and control instrumentation for energy infrastructures. As an example, the overarching goal is that eventually not only create new algorithms, but also especially create an evaluation framework, including NS3 simulations and NSF fabric frameworks are some interesting cloud environments to test these things. So that will be an integral part of this project, because we believe without a good performance evaluation framework, it will be difficult to justify the merits and innovation. So that will be an important focus. At the end, we believe that this satellite ground communication backbone can benefit both civilian and military aspects, including NATO and many other civilian applications are in consideration. So this is about the NSF projects that we are working. Let's move another with Army Research Laboratory, another collaborative project. So this is additively manufactured multi-dimensional cryptographic solutions with physical unclonable function support. So basically, this project is between our electronic department. They are creating from scratch PUF-based sensors at the manufacturing level, and we are integrating new cryptographic solutions to make things more lightweight. What are the research challenges and use cases? Our use cases is classic IoT with smart home, smart car, and smart city systems. And as we know, these kind of systems has limited battery, limited CPU up to 8-bit, low-level CPUs, and very limited memory up to maximum kilobytes. So even if we are using symmetric key cryptography, large number of devices and large number of transmissions is still a significant problem. Another issue that we need to talk here is the lack of forward security and aggregation in standard symmetric crypto techniques. The smart homes, the smart airports, if somebody go, they can open up and even compromise the key by physically, or a malware infection can also expose the cryptographic key. So the forward security, which is a key evolving technique, is very important, but not explored in this domain sufficiently, we believe. And can we add signature and tag aggregation capabilities, error correction codes, so that system become both compact and resilient is another research challenge. And finally, to the best of our knowledge, is hardware, software co-design with these unique capabilities is an open problem in the literature. The overall objective of this federal project has been to create ultra-lightweight symmetric frameworks for embedded IoT systems. The current technical framework that we have been proposed has been a graphene framework, which is we call it graphene because it's a carbon-based molecule, which is both lightweight and resilient. That is why we call it graphene. And recently we extended into diamond framework. At the technical heart of our algorithms lies universal message authentication codes, which are algebraic UMAX and pseudo-random functions that exhibit homomorphic properties. By utilizing these techniques, we have created specially tailored algorithms for IoTs, including offline-online MAC capabilities, algebraic aggregations, and amenability of threshold techniques. This project has yielded 3 publications and open source cryptographic framework that you can download and test on your framework. We have tested on 8-bit medical devices and small air drones, electronic control units. We have tested on 16-bit, which are typical against some embedded devices, ARM processors, which are typical in airports, and of course, commodity hardware. So we can provide you links and you can just download and test. Finally, given the little time remaining, I wanted to switch the gears a little bit into post-quantum and AI. The cancer detection is always very important topic. And one of the important aspects of that, a textbook use case of secure multi-party computation is we have the hospital, we have the university, we have the cancer centers, they have their own data, private, legally protected. If they could exchange information without disobeying the law, imagine how good private diagnosis or joint drug discovery would be. A textbook use case of MPC, let's use machine learning and MPC to make it happen. Unfortunately, due to its expenses, this excellent use case hasn't been in practice. And it will be very, very more expensive if we consider with radiomics, because some has ultrasonography, some has computer tomography, some has MRI, different image formats. A joint diagnosis is a very difficult thing to achieve even without MPC, let alone MPC. And when you move to distillation and across different institutions, many scalability issues come. Our goal right now, which we are trying to develop with Moffitt Cancer Center and various institutions, can we create a private and trustworthy cancer detection framework that is post-quantum secure? Why? Because long-term security is very important in medical domain. What kind of innovation we target? We believe to achieve a successful breakthrough in here, we need innovation at signal processing, quantization, and linearization level from mathematical foundation, as well as lots of architectural innovations that optimizes the MPC for radiomic techniques. Eventually, we hope we will be able to implement and deploy this on USF and Moffitt Cancer Center infrastructure. That will require a lot of IRB efforts, obviously, but we hope that if we can achieve, that will lead to important breakthroughs. And with this, I would like to leave some time with the questions. Thank you very much for your time and the opportunity again. I will be very happy to take questions if there is any.
Thank you so much, Attila, and for a great set of updates and talk on the quantum subcritical national infrastructures. I think we'll move on to Professor Jaideep Vaidya, who is a distinguished professor at Rutgers University. He'll be speaking on trustworthy AI/ML in the post-quantum age. That's a very important topic, and thank you so much, Jaideep, for your time and presenting at the summit. Over to you.
Thanks. So thanks, Ashish. Hopefully you can see my screen
Yes.
now.
Yeah. If you can make.
Yes.
Thank you. Yeah.
I think it should be visible now. Actually, Attila has provided a fantastic segue into what I want to talk about next, which is, again, how, the post-quantum age, basically quantum computing, quantum cryptography, has an impact on trustworthy AI and ML. And again, I want to thank you, Ashish, and Cisco for giving me the opportunity to speak at, of course, this important PQC summit. So the premise, what I want to talk about is not just from underlying protocols perspective or specific elements. The premise itself is that AI or AI/ML is only as trustworthy as its overarching, underlying assumptions, if you will. We talk about AI, we talk about AI/ML as a single thing, but really it's a very layered system with a lot of different elements behind it. And of course, as you can imagine, what happens with quantum computing, we need to worry about the underlying assumptions that are in place and what happens there. So essentially, we are considering today that the data that is being used for these AI/ML systems, that is secure in some form or shape, and I'll go into more detail on this in a while. We are also assuming that the computation, when we are training these models, whatever it is that we are doing, this is trusted in and of itself, that it is actually being calculated or being correctly done in and of itself as well. And then, of course, that the outputs, the models that we create, and the way we use those models is also done in a reliable way in and of itself. And the issue, of course, is that all of these underlying sort of systems or elements, all of these assume classical cryptography. So essentially what happens with quantum computing and the post-quantum age is that we need to rethink what does it mean to be trustworthy in this current era, particularly going forward from an AI/ML sort of perspective. And that's what I really want to talk about today. So just to quickly touch base on what, of course, is considered to be trustworthy when we talk about AI/ML today. And these are things that you can think of. Attila briefly touched on privacy, very important, especially when you think of using AI/ML in applications where the data is sensitive, like for healthcare, or in other settings, financial settings, and so on. And you absolutely need to worry about the privacy of data. And we might be using tools such as differential privacy, multi-party computation, what have you, to maintain privacy for AI. You, of course, also need to worry about security in an overarching sense, because we have to worry about the trustworthiness of the models, whether there are data poisoning attacks, or malformed models or what have you in and of itself. So security is another implication over here. And then, of course, we also have issues related to fairness, if you will. where you want to make sure that whatever models that you're building and that you're applying are done in as a representative fashion and applicable to the world at large, to all populations, and so on. And finally, we have to worry about accountability as a whole as well, because this is not a one-shot sort of thing where you take a single use case, you apply something, you get an output, you're kind of done. You need to make sure that everything that goes into it, all of the data that was used to create the underlying model, the decision points that are used to come up, the data points, I should say, that are used to come up with a decision, these are all trustworthy, and how you operationalize the decision, that itself is trustworthy as well. So all of these factors really come into play. Now, the interesting thing is, does all of this, break under quantum computing? That's not true, right? So what changes really with quantum? And clearly, some things actually stay stable while some are disrupted. So if the simplest thing that I can talk about, we have notions like differential privacy, which are currently information theoretic, if you will, the basic notion of differential privacy. If we are creating models that have a differential privacy guarantee, that actually stays stable because the guarantee itself is information theoretic. But there is a nuance to this as well. And the nuance in this particular case is that even though the guarantee itself is information theoretic, the way it is actually being operationalized may be vulnerable to attacks in and of itself. So we have to make sure that the way it is operationalized still is secure in the post-quantum age. And the second interesting factoid, which I won't go into in too much detail right now, is that traditional or the standard differential privacy is, of course, information theoretic, but you also have notions of computational differential privacy where they rely on computational assumptions, and this, of course, becomes vulnerable in sort of quantum settings as well. But nonetheless, we can think of the core model itself at least being stable in and of itself. Then issues such as fairness are also, if you think of things in terms of statistical models, that's also fairly stable. We don't necessarily need to worry about this. What we do need to worry about, of course, is encryption. And why does that matter? That matters from an authenticity perspective. And I'll come back to that in a few minutes. And then, of course, secure computation that Attila just talked about. And I'll actually talk about that a little bit more. But that actually is a huge deal. This really, we have to redesign what we are doing completely if we want to make sure that this works in the post-quantum age. And then, this notion even of authentication and trustworthiness across everything is very important, because you have to take into account not just the fact that we are building these models, but that they are being used in actual settings. And there you have to worry about these system level issues, not just, again, as a single instance or a single problem in and of itself. So again, if you consider the AI pipeline as a whole, right, going from data over here to training to model to deployment, we actually see a post-quantum risk at all of these different stages. Of course, the risk may be different. We may be more worried about integrity in the data stage, while we are worried about, say, the secure computation aspect of it during the training stage. But we have to worry about provenance for the models and even authentication at the deployment stage. And all of these are vulnerable to post-quantum, or rather vulnerable to quantum computation, if you will, and need to be sort of resilient or hardened in the PQ8, so to speak. So let me briefly talk about this. I actually will not spend too much time on this. Ramana talked about this. Ashish, you talked about this at the data layer. One of the immediate risks right now is the harvest now, decrypt later. And that, of course, is an issue. You have to worry about the data and how it is protected before it is fed into the model. But I won't touch too much on this. I'm actually going to talk slightly more about the fact that we really increasingly need these authenticated data sets and provenance of models. And when you talk about provenance, especially when you talk about changes that may happen, pre-processing of data that happens, changes, aggregation of data, creating these clean data sets, this provenance itself has to be post-quantum secure in and of itself. So this is pretty critical, and we have to move towards authenticity of data and models, if you will. One last thing that I'm going to talk about here is this issue, interestingly enough, even of synthetic data. We know that AI/ML works really well as long as there is sufficient data, right? And we've used the data that is already out there. So really, in a lot of different settings, we are moving to synthetic data. Synthetic data will completely overshadow real data in AI models. And this data, of course, has to be representative, realistic, and high quality. We've done some work on this as well, which was presented at different places, which shows how we can maintain this representativeness. That itself is not the problem. Again, the issue is when you talk about synthetic data, because it is generated, you have to worry about how accurate this is, and can you, provide some guarantees for where this data is coming from. Otherwise, people can make things up. They can be used to poison, what happens next, and so on. And all of that has to be made sort of post-quantum secure in and of itself. So I think this is a very important aspect that's going to come up as we sort of go along. At the training layer, I'm going to talk about just one thing. Again, and Attila touched on this as well, that if you think in some sense, if everything is being carried out in-house at one spot, we don't necessarily need to worry, in and of itself. But if it is distributed in any way, multi-party computation, federated learning are both affected in and of itself over here. So the underlying cryptographic assumptions are changing. And to begin with, this is, considered a huge issue from a scalability perspective. You move things in from, again, the standards that we have. Essentially, it becomes much more expensive to go ahead and do this. And that's going to be an issue when we want to get this out in the real world in and of itself. So we have to inherently take into account that not only do we have new trust models, but we have higher cost protocols that are being sort of put together. So effectively, again, we may see a shift to sort of verifiable computation. And then if you're doing stuff like this, you have to make sure that you're using the right approaches to do this in as lightweight a way as you can. So one of the things that I did want to spend slightly more time on is this notion of federated and distributed AI. People don't realize it, but distributed AI is everywhere in and of itself, and it's not just a matter of the data itself being distributed. In fact, the model itself may also be split or may be applied in different ways. So I just wanted to briefly touch on some work we did actually for the US-UK Privacy Enhancing Technologies Prize Challenge. This was specific to this issue of transforming financial crime prevention through privacy-preserving federated learning. And I won't go into any of the details on that. We actually published, we won the first prize in the competition for this work, which was announced by the White House in 2023. The work was published in the Transactions on Privacy in 2024, where it received a journal-wide Best Paper Award. But the key idea was that you can take the data across the different sites and again, put it together. You can aggregate it in a particular privacy preserving way. We are using tools such as distributed Bloom filters, encryption, a bunch of different things, and then also you creating some augmented models that utilize differential privacy to sort of provide this guarantee. And it was very lightweight. It actually works very well. But remember, it is all based on classical cryptography. So now, if you want to move this to the post-quantum setting, life becomes much more, not difficult, but nonetheless, you have to take into account that even when you use it, the authentication itself changes, not just the fact that the aggregation has changed before and things of that nature. So there are a lot of PQ challenges, in terms of secure aggregation, the authentication that I touched on as well, that I won't go into for the sake of time at this point of time. But that is, I think, where we need to go if we really want to make this robust and usable, not just today, but 5, 10, 15 years from now. And then integrity challenges as well, but I'll come back to that in a minute. So one important point that I do want to make, you've sort of taken things together, you've built models, if you will. Now, if you want to sort of operationalize this, there are questions of, can we trust that model itself, right? And we've known issues with respect to security, things like backdoors or poisoning, the pipelines may be tampered with in some way. There may be bad data, there may be bad pre-processing steps that are actually happening. Maybe fine-tuning of models is happening in a particular different way. Essentially, there's this problem with unknown sort of provenance. And there are some solutions, right? There are solutions to this that kind of track every single thing that happens. And in fact, not just tamper-proof logs, so to speak, but perhaps even sort of mapping this onto the blockchain, where you're keeping track of precisely what changes happen. What is the authenticity of all of this? What are the different steps that actually happened? But the problem is, under quantum threats, you have to move this. Even when you consider blockchains, again, something that Attila mentioned, we have to worry about this. And I think Cristina is going to talk more about this later on as well. You have to make sure that it still works under this setting. So you have to incorporate things like model verification or secure engravings, or even behavior-based auditing, which is not necessarily, directly related to PQC itself, but makes it reliable as a whole in that particular setting. So I think this aspect of things is very important as well. I did talk about the fact that differential privacy in terms of privacy remains strong, and that's basically great, at least for classical or the standard differential privacy, but you still need to worry about composition with other PQ systems and new leakage channels that sort of show up. And the reason for this, again, is the way things are operationalized. The guarantee itself is fine, but the way you're providing that guarantee, actually, if you're generating random numbers, if the random numbers that you're generating are not quantum secure in and of itself, then the guarantee doesn't hold, right? So it's a systems level thing, not just a pure mathematical thing in this particular case. And I did want to talk very briefly about some extensions of work that we've done. There is a lot of work on extending differential privacy. One of the things that we did was to create a tailored version of differential privacy called sensitive privacy, which actually provides much more utility or accuracy for specific applications. So this is great. Luckily, this does not depend on sort of computational assumptions, because if you use computational assumptions, then those also have to become post-quantum secure in and of itself. So I think, the issue is underlying computations that may be used, you have to question whether they are actually, still valid under the new setting, under the new problems that we face. And again, you can look at some of the work that we published at CCS and TKDE with respect to this, but I think this will become very interesting going forward. I'm going to just spend the last couple of minutes sort of talking about our vision going forward, right? Like what is sort of trustworthy AI in the PQ age? One of the things that both Ramana and Elisa very much talked about was this notion of agility. And I think, Ashish, you mentioned it as well. In fact, that was the title of what you were talking about, that all of our pipelines have to be crypto agile, and this is really, really important, because especially for something like AI, it's not a single artifact. It's really a much multi-layered system that is dependent on so many different things. We have to move to a systems trust kind of model. We have to look at this from an end-to-end setting, right? So going all the way from the data to the training, to the models, to their use in distributed settings as well. So we need crypto agile pipelines, and we have to integrate all of this. We have to make sure that we are able to provide some guarantees for the AI/ML models. It has to be verifiable. And even if we are considering aggregation, we need post-quantum secure sort of federated learning. And that becomes difficult when we are talking about multimodal data, if you will, as Attila was mentioning, not just radiomics, but even if you think about genetic data. We have some ongoing work with Case Western University and the University of Texas Health Sciences Center at Houston. And we are actually precisely trying to do this because you have very large-scale studies. And if you go through IRB protocols, they take a lot of time to actually go through. So can you create sandboxes where you can get sort of, understand the value of this? which can provide as supplements to the IRB to then let you go and actually calculate this in real life. So there are some very interesting questions from that perspective as well. And then, Dustin talked about the NIST, the PQC framework, the standards. We do need to move towards standards, but I would say we need to really broaden these standards as well. We can't just be focusing on single protocols. We have to talk about systems and frameworks that are even AI-specific post-quantum frameworks. So we really need to, have some sort of end-to-end certification of this entire process. And I think that is really the key message that I would like to provide. That's where we are moving towards. And that is what we want to achieve as a whole. And it's possible, it's doable, it will require work though. It requires work at sort of all stages of this. All right, with that, I'll actually stop for questions, or we can move on, so to speak, and then come back to questions at the end.
Thank you so much, Jaideep, for taking us through your vision of quantum resistance and AI/ML and the challenges you mentioned. So we'll, in the interest of time, we'll move to the next talk. Professor Cristina Nita-Rotaru, who is a professor at Northeastern University. She is going to talk about quantum disruption, how post-quantum attackers reshape blockchain security and performance. That's an important topic given the cryptocurrency world and also the blockchain world, and there's a lot of discussion going on in the industry. Thank you so much, Cristina, for your time and speaking on this topic. Over to you.
Thank you very much. Thank you very much, Ashish. I am happy to be back. I participated in this event last year, and I was very informative, and I got a lot out of it. I'm also the last speaker, so probably some of the information, at least in the beginning, might be a little bit repetitive, or maybe just summarizing what some of the other speakers have already mentioned. So to start, right, we think about data, right, in three phases. We think about data being stored, so that's data at rest. We're thinking about data moving between different components. This is data in motion. And also about data in use. In fact, I think some of the things that Jaideep was talking about is data in use. When it comes down to data in motion and data at rest, we do have today well understood solutions. I think that for data in use, there is still work that to be done, but at least for storing and transmitting information today, we have standard solutions, right? We have standard protocols like TLS or QUIC that allows us to move data securely on the internet. And we do have encryption algorithms, most of them based on symmetric keys, and where these symmetric keys are encrypted under public keys. And security for these solutions comes from cryptographic primitives that assume computationally bounded adversaries. And as it was iterated through by all the speakers today, these assumptions are disrupted by quantum computing. We have today algorithms that will enable quantum attackers to break the primitives that we rely today for security, in particular RSA, ECC, and Diffie-Hellman, or weaken significantly symmetric encryption. And in fact, there were some new results recently that showed that the resource estimates for breaking the 256 EC discrete log, it's actually lower than it was originally estimated. And while we do not have quantum computers, right, we do have attackers that might think about storing the data now and decrypting it later. And this is why we're all talking about how to design and deploy these quantum resistant algorithms. Now, what applications are going to be impacted? Pretty much all of them, even the ones that think that they're not going to be impacted, they will, because the security ecosystem is very connected today. And if you're relying on some form of certificate authority, public key identities, you will be impacted. So this includes the way the internet security, banking, messaging applications, cloud security, and last but not least, blockchains and cryptocurrencies. And as Dustin was mentioning earlier, NIST took a leadership role in actually standardizing several algorithms to prepare the entire community for what is coming. And we have several standards for digital signatures and for key encapsulation, right? There we have one, and there is another one considered. And also, as Dustin mentioned, there are very clear now transition recommendations, the regulatory timelines in terms of when migration should happen, and most importantly, deprecation timelines, right? It's by 2030, RSA ECC deprecation, it's starting. So clock is ticking. That's not that really far away. We also have advancements in terms of deployment. There are libraries that already implemented these algorithms. We have standards for protocols with hybrid implementation. This includes both the open source, but also proprietary protocols such iMessage, for example. And the technical challenges lying ahead are diverse. First we have been using the current cryptographic primitives for a very long time, right? RSA was created in the 70s, Diffie-Hellman similarly. So we have a good understanding of their attacks, but with respect to these new PQ algorithms, there is less information. So there are some concerns. There are new side channels, vulnerabilities that are happening. And also, we don't know very well how the applications are going to be impacted, because the current algorithms that we have, they will require significantly more computation resources, storage resources, and bandwidth resources. And last, as Elisa was mentioning at the beginning of the talk, we have many devices that are very limited. So it's not very clear what's going to happen with them. So in this talk, I want first to summarize very briefly some results from the talk that I gave 1 year ago, because it fits with again, re-emphasizing why we have to be very careful how we are designing and applying these PQ primitives. And second, I want to focus on blockchains as an application that we recently looked at and examine how it's going to be impacted by post-quantum attackers and what plans are in place to address them. So first, together with Ashish and Ramana here from Cisco, we actually looked at existing PQ primitives, and we wanted to understand, given that they do have significantly different footprint in terms of memory, computation, bandwidth than traditional PQ, how easy is to classify them or to distinguish between them? And we ask these questions in many different flavors. Can we distinguish between classical and post-quantum algorithms? If I give you a library that implements different PQ algorithms, can you distinguish between them? Or can you distinguish across implementations, across libraries? Similar for key exchange, can you distinguish it with respect to classical? Or if I give you different algorithms using different key exchanges, can you figure out which one it's used? So the table here shows the key exchange classical versus PQ. And as you can see from the numbers, they're all very high. So while this in itself is not a vulnerability, it's actually something to be aware because there are many attacks that start with reconnaissance, right? Like figuring out what algorithms are used by the systems that are going to be attacked. And this is a paper that will appear in SACMAT in like a few months, in I think July. The other thing that I wanted to talk about is this notion of side channels that don't always appear where you think that there is very obvious that they will be there. So what happened several years ago, we did some work where we looked at a new scheme that was proposed to address confidentiality when you have post-quantum attackers, where the way confidentiality was achieved was by using multiple paths between a sender and a receiver, and splitting the message that was supposed to be sent in different shares that are sent on this path. And this path will change with every new information that is sent. And this scheme was actually shown to provide information theoretic security. So it seemed that will have very nice security property. And when we look at the scheme, we wanted to actually create a system based on it. What we observed in our implementation is the following phenomenon. So what actually this graph shows is how many paths were active in a real network. This was a software-defined network-based implementation. How many paths were active? In this case, we were using a system with where 5 paths were used for every dissemination, because there were 5 shares, right? But the total number of paths was 9. This is what the 5-9 means. And so ideally, what we thought that we will see is that most of the time there are only 5 paths, but that was not the case. As you can see here, there were 6, 7, 8, 9. And this really created a network side channel, because what that meant is that packets that were supposed to be captured by an attacker, there was only 1 chance. Now there were more chances because these packets actually lingered longer in the network as new information was sent. And then in the end, what we actually understood in the process is that the theoretical results used the well-known model. So it's not like they made strange assumptions, but these assumptions are not realistic when we look at implementation. And that assumption was basically that each network path, it's a wire, and that all the disseminations of messages on all these different paths take the same amount of time. It's either the same latency or the same number of hops, and that obviously was not the reality. So this is something that we published a few years ago. We really showed how this side channel actually could have been exploited to break the scheme, and we proposed some mitigations techniques. So this is like summarizing some of the older stuff. But what about blockchains? So since I know that this talk is also for like a more general audience, I thought that maybe I should give like very short introduction on Bitcoin, which is basically a digital currency where a set of peer nodes that participate in the system maintain a ledger. And this ledger is supposed to keep track of all the transactions that were consummated in the network. And the way the transactions are written in the network is in the form of a block. Now, all the peers need to agree on what this ledger is, and the transactions that are added need to be validated, to be considered, to see that they are correct, that there are correct signatures on them. Whoever it's doing them, it has ownership of what they're doing. And in fact, the way this ledger looks like, and that's where also the terms of blockchain comes, is that we're never writing one transaction. You actually write a block of transaction, a set of transactions, and this set they're put in a block. And these blocks are chained such that an attacker cannot change information in the past. And the way a block is created is through a protocol that is known as proof of work. It is at the core of the way the nodes in the network will obtain consensus. And what really means is that at any point in time, all the peers would like to win that they are creating this block with transactions. And the way they do that is by solving a cryptographic puzzle. It's a hash-based cryptographic puzzle. And this what they really obtain as a result of the cryptographic puzzle is actually the identifier of the new block. And they also get some incentive for doing that. This scheme has as a main goal that it mitigates Sybil attacks, where an entity may create fake identities and thus control what the output of the ledger would be. And it also shifts the assumption from a number of votes assumption, which is more traditional, which happens in more traditional consensus algorithms, versus here it will be an requirement or an assumption of hashing computational power. We do not want the attacker to have a majority in terms of computational power. So in our work, we actually consider 7 systems, and we can extend it. The systems that we consider were Bitcoin, Ethereum, Algorand, Solana, XRPL, Monero, and Avalanche. And we selected them, some of them because they're really at the top of list in terms of the value that they have, right? In terms of the money that right now they have, for example, Bitcoin, Ethereum, Solana, XRPL. Others we selected because they have different properties, like Monero, for example, it's a private chain. Avalanche is a multi-chain. So they gave us different dimensions that we could look at while we were doing this work. And the questions that we ask are, what are the cryptographic building blocks that they use? What solutions have proposed? What the impact is on the system? So here we did exactly what I think right, Ramana and Ashish were saying at the beginning. It's like, well, you have to go and check to see what is your cryptographic exposure, like what cryptographic building blocks are used. So in the context of these systems, we look at documentation and code. And as you can see from this table, they are all using, with the exception of Algorand, the ECDCA signature. And some of them are also using SNARKs, and they're using VDF or VRF that also provides some exposure to quantum attackers. Then we wanted to see what is the take of each of these, all these algorithms have behind them, right? Foundations or organizations, companies, how seriously they take this quantum computing threat publicly, right? We have access to public information. And you can see that in terms of safeguards right now, most of them do not consider. Algorand and Solana are the only ones. They are all exposed. Most do not have transition plans, but many of them seem to have some ongoing research in terms of being aware that they do have to do something about the fact that they are using cryptographic building blocks, that they're vulnerable to quantum attackers. We also wanted to play with some what-if scenarios in terms of what will the impact be on performance, assuming that we can magically change these systems. And as I'll see, it's not so easy to change, some of them at least. But assuming that you can just replace the current digital signature algorithm with a post-quantum signature algorithm, what will the impact be, for example, on throughput? So we look at the theoretical transaction per second. Here you can see in the table on the left is the current theoretical versus on the right, the post-quantum theoretical. And for several systems, you see a very significant degradation. Bitcoin will go from 15 to 2. Ripple, for example, will go from 3,400 to 510. And there are several systems for which we cannot estimate. And the reason is because they will require very significant design changes. The current transaction side, for example, cannot accommodate the size of the digital signature. We also look at storage, which is a little bit easier in a sense, because there, if you just think that we're going to substitute all the signatures with an MLDSA 44, that really means an increase of the storage for about 35 to 40 times versus what it was. So these two tables, the one on the left shows the storage requirements, either for the full ledger or for the pruned version, when classical cryptography is used, while on the right, you can see it with the post-quantum cryptography. And again, just taking Bitcoin as an example, it's easy to see by looking, for example, at the pruned version, you go from 10 gigabytes to 400 gigabytes, right? So it's almost like a 400 increase. And this is consistent across all of them because it's the size of the signature that will dominate this cost. We also were curious about what implications will be on consensus. So this is the core, right, of the system. I talked a little bit about proof of work, but there are several other algorithms. Proof of stake is where the validators are chosen based on who are the nodes that have the most stake or most money in the system. Proof of authority is where you select a set of pre-approved trusted validators. Or you can have proof of history like Solana, where you can create a verifiable timeline of events such that you do not require all the nodes to have continuous or constant communication in order to obtain the same information about what happens in the system. And here are a few things about what's going to happen with the convergence of the consensus. We do need to look at this in more depth, but the short story is that all these post-quantum schemes, they have bigger signatures, bigger keys. This is going to result in larger block sizes, which will lead to slower propagation across the network and longer verification times. You are going to have nodes falling out of sync. That means is that consensus is going to take longer to converge, and we are going to have amplified events such as forking, for example, where you have more blocks that are going to be orphaned. What that means in terms of financial incentives is that you are going to have miners that will have lower expected income, right? As we have more orphans, and also this will reduce the profitability, which may push some of the miners out of the network, and also create more centrality, because, for example, miners that have like better connectivity or lower latency, they will have an advantage. With respect to open problems, how to do secure migration, I think it's a problem for all the systems, but it's particularly challenging for decentralized systems. You have to deal with making sure that you don't expose legacy keys, maintaining this identity and continuity of the system. If you are, while you're doing migration, make sure that you don't completely fall into centralization. Like, how do you keep this balance between scalability and how do you do this migration in a decentralized way? And last but not least, you will have a time when you will have these two type of credentials in the system. So you have to do this incremental deployment. The other thing that I think it's specific to blockchains is privacy. And here, in terms of solutions that we have today for quantum threat, there are very few. So first, that we need work and we need solutions that will be able to deal with quantum threats, right? We need to have these cryptographic replacements, which right now we don't. And this new work that needs to be done needs to take into account that the fact that there are different challenges across different architectures. For example, UTXO systems like Monero, they need to maintain strong anonymity and unlinkability. But then we have account-based systems like Ethereum or Solana, which they're much more their challenges are with respect to confidential smart contracts and composability. So to conclude, in case anybody was worried, blockchains will be seriously impacted by quantum attackers. I think that this is very obvious. Many of them do not seem to have a public plan in place, which is a little bit worrying, given that NIST already has these recommendations for deprecation of schemes that they are using. For several of them, fixing or dealing with quantum attackers is not just a simple replacement of existing cryptographic building blocks with post-quantum ones. They actually will need to make significant changes to their design. And last but not least, given the current computation and the communication cost, all of them will suffer a very significant degradation of throughput, increased storage, and unpredictable peer behavior. And with this, these are the two papers that I mentioned before. And with this, I am done. So we can start the panel or take questions. Thank you.
Thank you so much, Cristina, for the really important talk on cryptocurrency, Bitcoin, and the quantum safety. And I must thank all our speakers to actually sticking to the time and really appreciate that. So we have about 20 minutes remaining for the panel, and we are honored to have a list of distinguished speakers who talked about various subjects. Let me again share my screen to show the agenda here, so that we can revisit things properly. Yeah. So I'd like to start with maybe we can take just small break, maybe for a few seconds if you want to, but we can go straight into the questions. Okay. I think I'm going to let's have a set of questions prepared for Dustin. Again, thank you for your talk. One of the point is especially for lightweight cryptography and IoT devices, are there any specific focus? I know Falcon is something that NIST is focusing on, but any thoughts around that, if you could shed some light?
Yeah, lightweight's a challenging area for PQC. NIST has done a lightweight crypto project over the past few years and selected an algorithm called Ascon for standardization, but it's not public key. Most of the PQC algorithms would probably not be described as lightweight. Falcon does have the smallest signatures, but its implementation with floating point is quite complex. So that's still an ongoing active research area. There are some schemes proposed in the literature which are a little bit smaller. They haven't been as evaluated over a number of years like the schemes that were standardized. So we are interested in that direction, and it is kind of still an active area of research that we're keeping an eye on. Okay,
thank you. I'll go in the order of our speakers, and then we'll reverse back and so for Elisa, the questions I have is that in order to develop holistic quantum resistant networks, you mentioned about several dimensions. Do we have to address, does an enterprise or an approach need to address all the dimensions or some of the dimensions? If you could shed some light on that.
Yeah, that's an excellent point. They need to consider those dimensions, okay? Because otherwise, again, all aspects are important. Definitely, for sure, understanding at least the key distribution and the key life cycle management, those will be important to start. Because in several cases, especially actually when you deal with data, so if you look at a lot of DBMS which do full database encryption, they use asymmetric encryption. And this symmetric encryption key is encrypted with an asymmetric key very often. So basically there you need to deploy some combinations which may use a symmetric cryptography for the actual signature or encryption. And then you protect this key with asymmetric encryption. Or again, that in my view is very critical. There are many other important aspects which do not directly related to the key, but having a good governance of your data and understanding your system is critical, because at the end you will need to understand that some part will be strong under post-quantum, but others may not. And how do you have this collaboration between an untrusted component and a trusted component? That's kind of a zero trust, but more sophisticated, where you say, I have zero trust in some, but in others, I can trust more. So that will be critical.
Thank you. So there's a question from the audience for Dustin. Should we welcome the proliferation of PQ crypto options per jurisdiction? Each PQ option represents more testing, validation, and engineering investment. So, yeah.
Yeah, I'm not sure I caught what the question was exactly. Can you say it one more time?
Yes, yeah. So, should we welcome the proliferation of PQ crypto options per jurisdiction? I don't know what they mean by jurisdiction here. And each PQ option represents more testing, validation, and engineering investment.
Yeah, it's a good point. There's always a kind of a trade-off when you're considering standards. In general, for interoperability and adoption, you want to have few choices, because people don't like to have to choose between all the different options, and when you have to combine them, that can explode in combinatorial number of ways. On the other hand, it's hard to make one algorithm a silver bullet that will fit all use cases. So there is a little bit of balance there that you have to look at. We erred on the side of trying to choose just a small number. Right now we have 2 chems and 3 signatures. That may not fit all use cases perfectly, but we feel it will fit the vast majority of them, and it will keep the number down as much as possible.
Thank you. So let me move on to the next question to Attila. So you mentioned about MPC. So can you shed some light on, is MPC going to help PQC and quantum resistance, or is it also going to add some challenges in that process?
So I think it is both. It would very much help, because no matter what we do, the centrality problem will be there, and we need to mitigate the centrality issues. And MPC will allow us to manage keys distributedly and execute post-quantum algorithms in a distributed way. And while doing so, the beauty of MPC is it allows interchangeability, meaning whatever security guarantees you had in original algorithm, you will have it exactly if you do it with MPC. So these are the good part of that, and MPC itself can achieve post-quantum cryptography through linear secret sharing, guarded circuits, and relevant techniques at the ground can be post-quantum secure too. So these are the good parts of it, but the difficulty is that the MPC standalone is an expensive protocol, right? So it can be very communication incentive, computationally expensive. So when we integrate those, I think we should be very careful to calculate if the underlying application really meets the performance requirements when we consider distributed protocols. It's not only about MPC, in my opinion. Any distributed protocol, including use of the blockchains or any other consensus techniques, those do introduce communication and delay. So we must be carefully assess if the cost that we are incurring actually is acceptable for the applications. So that's the challenge that I observe.
Ashish,
Sure.
sorry to interrupt the protocol.
Yes.
May I make a comment and ask
Absolutely,
actually to
please. No,
Attila?
this is applicable to all
Actually,
the
Attila,
parties.
you touched a very good point because MPC is very expensive. But do you think in the future quantum algorithm can be designed to make MPC very quick? So which means we will use also for defense the the quantum computers. Do you have any idea?
So, I mean, there has been an initiative already about MPC in the head primitives in the cryptographic community about how we could create signatures that are MPC friendly. If Dustin would chime in, but there is actually some calls from NIST about how to create MPC in the head type of NIST post-quantum primitives is already a call and a very active research area already. So I think there has been block cipher-based signatures like Picnic that is a representative of exactly what you mentioned. And I think in the future that will be even more important. And NIST is on top of that as far as I know.
Great.
Yeah,
So we can, sorry, go ahead. Yeah.
just to add on to what he said, yeah, there are in our on-ramp process a few signature schemes like FACE, SDITH, Mira, RIDE, PERC that are using MPC and the head techniques to design signatures. It's a very active and ongoing field. Separately, NIST does also have a MPC in the head or a threshold call, many of which use MPC in the head techniques that NIST has an open call for submissions in this field as well.
Okay, thanks.
Thank you. This is a very great discussion. So one of the point I'd like to also mention here about MPC and the industry adoption is because of the expensive nature of the protocol, as well as that from a key lifecycle management, from a security management point of view, multi-party computation doesn't provide a simpler approach to the industry than what the centralized mechanisms do. And I think going forward, what will be more of a hybrid approach. If MPC solves certain problems, both centralized and MPC, we have to work together. If I look at the business angle and industry angle of adoption of that, and perhaps I think there's a need for addressing that, or maybe that is already addressed. Anyway,
maybe I can just comment.
Yeah, please go ahead. Yeah.
So Ashish, this was again a very good point. In fact, this is happening to some extent because pure MPC is fully peer-to-peer, if you will, and then you have, of course, the purely centralized version as well. But there are alternative approaches, where you can have some server-assisted work. There have been things of that sort that have been considered for quite a long while. And what we see increasingly is that you can have this asymmetric sort of computation capacity or even asymmetric data capacity where certain sites may have way more data, if you will, and then, as you said, a hybrid approach can actually be used in and of itself, and perhaps you can use that to improve things.
Thank you, Jaideep. Yeah, that's an important point you made. Now, since you are on it, I'd like to also have a question for you on AI/ML. Why model trust is important for the future of AI/ML, and how do you think the quantum resistance or the quantum threats can influence it in a negative way?
Thanks. I mean, this is like the can of worms that once opened won't close, right? So model trust is critical, as a matter of fact, because what we see is, one of the great things that has happened in the new AI revolution is that things work, supposedly. But the problem is that people don't know when or why, right? And model trust is really crucial because you need to know that things were properly done. So even if you don't have explainability, was everything trained over curated data in particular ways and so on? Are we using it for things that it was meant for? Because if any of those underlying things break, then even though it may work very well for in specific cases for certain subpopulations or whatever, the results can be completely different. And this, by the way, is even without taking into account malicious adversaries who absolutely can then try to actually modify things and again do things like data poisoning or do things like putting in backdoors and things of that nature. So given the fact that these models will be used in distributed environments, will be used in sort of low capacity environments and things of that sort, it is really important that we are able to understand whether or not these models have been correctly developed and all of the steps that have gone in order to make this happen. And the reason, coming back to the post-quantum setting, many of the ways in which we are providing these guarantees inherently are dependent on classical assumptions as of now. I mean, if you use blockchains to record things, as Cristina mentioned, that's not going to work, because in and of itself, if you can't trust the underlying distributed ledger technology, then of course, anything that is done using that is no longer going to hold. Similarly, even if you're worrying about the safety or the sensitivity of data and you're encrypting things before, you have to worry about what kind of encryption is used and how you're maintaining these things. So yeah, I mean, I think this is a problem that's there, and it is going to be there unless we address it, and it will become more important as time goes on.
Thanks, Jaideep. Okay, so if there are no further comments on this, I have a question for Cristina on maybe there are two of them because of the interesting topic of cryptocurrency. One is which cryptocurrency is closest to PQ adoption or is already quantum resistant? You are on mute, Cristina.
I think that Algorand was the only one that actually had the signature deployed, and they seem to have like the best transition plan. But we should check again. So this was when we finished the work, I think, at the beginning of the year. But if you look in the scheme, right, the only one that was not using ECDCA was actually Algorand.
And primarily, maybe that's because the founder is a cryptographer.
Yeah, well,
himself.
yes, yeah, of course, if you have cryptographers, well-known cryptographers being designers of the system itself, they're obviously following up what's going on, and they're aware. And I think also they were always focused also on performance. So yeah.
The other question I have there also is what is the top challenge priority that you think to adopt a quantum resistant wallet, cryptocurrency wallet? Do you look at wallets as well?
So well, I think that there is that most of them do have this challenge with respect to sizes, right? And so that, I think, is the first thing. It will tell you if it's just a simple drop in, you just replace the algorithm. And I know that you are talking about crypto agility, and we should support all of them, but it's not as easy to move from one to the other just because of these fixed lengths that exist in the design. The other one, I think that the big chunk of it is really the transition also.
Okay.
Yeah, like the thing that I was talking about, migration, and I don't think that people have thought very carefully. And cloud setting is different because there is centralization. And it is true that some of these systems will have some centralization. But in essence, if you look at Algorand or Ethereum, Bitcoin, they are decentralized systems. So how do you actually do transition there? It's like the internet, right? How did we deploy secure PGP or DNS security. It was done incrementally, and so you have to have an incremental plan. And how will that, evolve? I think that is a big challenge. To be honest, I was even thinking that some of them might end up, having like an entirely different system.
Okay. Yeah.
And not change what they have. Yeah.
Thank you. So given at the interest of time, we have only 5 minutes remaining. So what I'd like to request is when the, and maybe in the reverse order to speak one key topic that are something you have in mind for moving towards quantum resistance or quantum secure on a PQC. I'd like to also mention that I think this is the chance, this is an opportunity I had, is that to ask the questions to the professors rather than they have been asking questions to students and me. I was earlier, but I think so I'd like to maybe go in the reverse order of Cristina, and what is your one line what you think would be on top of your mind for this quantum security and PQC topic?
Yeah.
Sorry, I didn't mean to put you on the spot, but
no, so what I worry, as we all know, that is going to be here, but I do worry about a very long transition and messy period. That I think it's like, it's even if you have all these algorithms that NIST has been working on, right, to basically equip everybody with building blocks. If people do not think very carefully about the transition, you can have a lot of basically vulnerabilities during the transition time. I think that is it's a very dangerous if it's not done properly.
Thank you. Jaideep, next.
Yeah, so I'll agree with Cristina. I mean, I think transition needs to be handled very, very carefully. But I will add to that we are focusing on very specific things, as I kept saying, like protocols, which is fantastic. I mean, we need to do that, but we have to move towards the broader picture of systems as well in and of itself, which is what I know we are advocating for in and of itself. Because if you look at it again, back to the trustworthy AI sort of thing, we need quantum resilient systems, not just quantum safe cryptography. So, yeah.
Thank you. Attila?
Yeah, I agree that the transition will be challenging. I think one thing about the motivation, harvest now and decrypt later, we talk a lot about it. But to me, the lack of authentication and public key infrastructures are even bigger problem. But because we can do man-in-the-middle attack and create infrastructure damage. So to me, that should be the PKI is a very important point to be protected. And also post-quantum transition on cyber physical systems, especially energy delivery, airlines, critical infrastructure are being less discussed. Those are legacy systems, very difficult to change anything, let alone post-quantum cryptography, and they can create actual physical impact. They should be handled very carefully and as a priority.
Thank you. Thank you, Attila. Elisa, your thoughts on this topic?
And basically, I would say that we will have for a long time a very hybrid heterogeneous situation. So we need to understand how to deal with that. And from a point of view of research, I like to see a lot of more computer scientists, either in software programming languages, being involved in this area, because it's not just a physics problem. It's really a problem that involves everyone in computer science.
Thank you. Thank you,
And
Elisa.
and
Sure.
Ashish, can I say
Yes,
two
of
words?
course. Yes.
So one thing that I also wanted to draw again attention is that a group of us here created, exactly because we believe in these cryptographic resilient systems, we created this new ACM conference, PQQS, that its goal is to bring together the industry, the government, the academia, but also from the academia, people from the cryptography and the system side, to really solve this important problem. So anybody that is interested in these things, to keep in mind the conference, to submit to the conference, or to ask us how to get involved.
Thank you so much. Thanks, Krishna, for bringing this up. Yeah, it's very much. It's in November. First inaugural edition has been held in Bay Area, San Jose. So, Dustin, what are your thoughts on this topic?
In one sentence, it's hard to cover all the complexity that will be needed. I'd say prioritize and get to work, and I'll just keep it simple.
Thank you. I like that. Yeah.
What we are trying to do.
Yeah. So I think okay. So with that, I'd like to
Ashish, can you say your last sentence?
Sorry. Oh, my last
Can you
sentence.
also say your?
Thank you, Elisa. So my last sentence is, I think we also is that prioritize it and get to work in a systematic manner. I'm going to re-emphasize what Dustin said, and and in a systematic manner, and that's what we have been trying to do at Cisco, about to build a very simple framework but powerful, like crypto observability, resilience, and agility together, so that we can have a quantum safe future, all of us. And yeah. And please join us at SEMPQQS in November. Send your best papers or best work, or join us. We love to have you over there. And thank you so much, everyone. Dustin, Elisa, Attila, Jaideep, Cristina, and Ramana. I think Ramana had to go. I couldn't ask him a question. So maybe I'll discuss it with him later. But thank you so much, and thank you so much to Carla and Kim for helping us get it organized and have it. And thank you everyone from Cisco for all your support, and the senior leadership team. Thank you, Vijay, our SVP at Outshift, for supporting PQC and quantum security work over all these years, and to Ramana as well. And thank you for our attendees. Bye now.
Thank you very much.
Thanks.
Thanks.